Okay, so welcome everyone. Today we're very happy to have Ben Lehmann from MIT. He will talk about broaden direct searches for light dark matter.
All right, thank you. So I am always focused on dark matter. It's not always in this context. I like to think about many kinds of dark matter, as I had the pleasure of discussing with some of you at lunch. But for the purposes of this talk, I want to focus on what I think is one kind of concrete frontier for dark matter physics that I think is going to be very much accessible in the next 5 to 10 years. And that is direct detection for what I'm going to call in this talk light dark matter. Now, if we're talking about dark matter, I have to start off with some context for dark matter physics, the state of where we are today. And we have to begin with the WIMP, because that was, for many years, the de facto dark matter candidate. We built an enormous experimental program designed to probe WIMPs as a dark matter candidate. And I want to just summarize what happened with that program. This is a review from a little while ago. I'm just going to read you the last line of this abstract. It says, the moment of truth has come for WIMPs. Either we will discover them in the next 5 to 10 years, or we will witness their inevitable decline. Well, this is a little more than 10 years ago. No WIMPs yet. So now we're used to seeing titles a little more like this. And I want to be very clear about this. The WIMP is not dead. There are certainly viable portions of parameter space. There are certain searches that absolutely need to continue. But there is broad agreement in the community that it's time for us to be more open-minded and to consider other possibilities. And there are two broad strategies for doing this. One is what I would call model-driven, where we identify certain lampposts, certain portions of model space that look really promising, that solve multiple problems. The other is systematic, is model-independent, where we develop a set of probes that we think is capable of surveying a large parameter space, and we develop those experimental probes. I'm going to focus mostly on the second of these two. We absolutely need both. And to justify that statement, I want to remind you what we are up against. This is one slice through the dark matter parameter space. This is just the mass of the dark matter particle. This spans 90 orders of magnitude. We have spent most of the last 40 years probing that red band, WIMPs. And there are lots of other islands here that are of interest that I know many of you have worked on. For the purposes of this talk, I want to focus on this yellow region. That's what I'm going to call light dark matter. So the kind of classic candidate to have in mind here, the simplest deformation you could make to the WIMP scenario, is to have dark matter freezing in, being produced out of equilibrium from the standard model. And in principle, this range can span from the GeV scale, where the WIMP peters out, all the way down to the KeV scale. Now, I want to give you a sense of what we can do for direct detection, where we've kind of come in the last few years. So here's what I'm going to do in the rest of the talk. First, I'm going to talk about how dark matter interacts in condensed matter systems, and how this gives us certain new capabilities and new kind of control handles to study dark matter physics. Then I want to walk you through how we can actually use a data-driven approach to really take what we know about materials, what we know about dark matter models, and stitch these together to make new and sensitive experiments. And finally, I want to actually show you real results from a set of experiments that my experimental collaborators have built in the lab. There are real constraints on dark matter, but more importantly, these prototype experiments have given us a sense of what we can actually do. It's given us some surprises, even some new capabilities we didn't think we would have. So let me get started by situating this sub-GeV mass range for you. If you look at a constraint plot from a direct detection experiment, you always see something like this, where the mass is on the horizontal axis, the cross sections on the vertical axis, and at low masses, you lose sensitivity. Why do you lose sensitivity at low masses? You can think about this as kinematics. When the dark matter mass becomes lower than the mass of the target that it is scattering with, it can no longer transfer energy efficiently, and you lose sensitivity. If you look at typical direct detection experiments that were built to study WIMPs, you will see that this cutoff shows up at around a few GeV. And the reason for that is that the experiments are built out of nuclei. Nuclei are tens of GeV. Now, that's an unfortunate coincidence. We'd like to go down another 6 orders of magnitude from here, not just because of the model space that's there, but also because there's actually a firm guidepost at a KeV. We know that if dark matter is mainly fermionic, it must sit above the KeV scale. It's very hard to wiggle out of that bound. Of course, you could have some light boson being the dark matter, but even if you had that scenario, I'm going to argue that the kinds of experiments that I'm going to tell you about are also the right way to probe light bosons that are not showing up in resonant cavities. So this is the situation. We want to get from a GeV down to a KeV. We want to look for the scattering of some particle in a detector. And one obvious way to do this is to use a lighter target. Instead of using nuclei, to use electrons. Electrons are MeV scale. And indeed, if you use present-day experiments and you look for scattering with electrons instead of scattering with nuclei, you will see that you can get limits on dark matter that goes down to a mass of about MeV. If you try to go below there, you encounter a serious problem, which is that you can no longer treat the scattering process as free particle scattering. For dark matter masses below an MeV, now the potentials in the condensed matter system that you are scattering with are big enough that you can no longer ignore them. So you should think about the dark matter detection process not as a scattering process of 2 particles, but as the detector making some transition between 2 eigenstates mediated by the dark matter. On the one hand, that is very annoying. It's very messy. It means we have to understand the detector's eigenstates to make a correct computation of the dark matter's interaction rate. But I also want to highlight that this is a real opportunity, because if we understand those eigenstates, we can actually take advantage of materials physics and even design detector systems that are optimally sensitive to dark matter. And now let me show you how to do that. So first, I want to situate for you how we can think about dark matter scattering with electrons in condensed matter systems, where we can't ignore the potential in the material. So there's a really simple idea about how to do this. And it's just to separate the probe potential, the dark matter's interaction potential with us, from the response of the condensed matter system. So we're going to have 2 functions here that describe an interaction. One is the potential that ordinarily shows up between 1 dark matter particle and 1 electron. And the other is some function that encapsulates the response of the material system to the deposited momentum and energy. It turns out that epsilon is literally just the dielectric function of the system. It is the same epsilon that you know from introductory E&M. It's just a Fourier transform has been done, so it has energy and momentum dependence. But that epsilon, the ratio of the applied potential to the total potential in the material, turns out to describe the entire response of the electrons in the material to any perturbing energy and momentum, as long as that perturbation is small.
Independent of the mediator.
I'm going to get there in just a second. Notational note. I'm always going to use Q here to mean momentum transfer and omega to mean energy transfer. I'm going to use that throughout the talk. So I really want to highlight that you have intuition already for this epsilon. And there are certain phenomena that you know from first-year E&M that actually port over to dark matter scattering. In fact, there's an analog of screening that I'm going to show you. Now, what do you actually need to do to make this work? You can write the dark matter scattering rate like this, where you separate out the ordinary 2-particle potential V, where the particle physics lives, from, in blue, this condensed matter object, the loss function, which is the imaginary part of -1 over epsilon. What I have secretly assumed in writing it this way is that the dark matter couples directly to the electron number density. So in practical terms, this means if you have any kind of scalar or vector mediator in the non-relativistic limit, this works. If you have some kind of tensorial mediator, if you have some spin-dependent scattering, this can break down. So my assumption here is spin-independent scattering, we couple directly to the electron number density. Now, having done that, there are a few key advantages of this way of writing it. First of all, it's predictable. We know how the dielectric function epsilon behaves. It's been studied by a generation of condensed matter physicists. We have lots of analytical approximations. We can actually go and measure it. We can use this in an empirical way. We can calibrate against either direct measurements of that dielectric function that we measure with standard model probes, or we can compute it using sophisticated DFT tools. And finally, this formalism is intrinsically anisotropic. That epsilon object, I've written just epsilon, but really secretly it's q hat dot epsilon dot q hat. That epsilon is a tensor, and it can have a directional dependence. Why is directional dependence such a big deal? I'm going to harp on this throughout the talk. Well, we don't sit at the center of our dark matter halo. Earth is somewhere off center. It's going around the center, which means that in the lab frame, there is a wind of dark matter particles flying through the frame. That means that as Earth turns, the dark matter detector is exposed to a different direction of incoming dark matter. So if the detector has an anisotropic sensitivity, if it's more sensitive to dark matter coming in this direction versus this direction, the rate is going to change over the course of a day as Earth rotates. And that, as it turns out, is an absolutely crucial tool for background rejection, for actually validating that you've made a discovery. So if I just had an isotropic experiment, I build it, I see some counts, how do I know whether I have found dark matter or not? It's very, very hard to argue that I have. And in fact, there are lots of experiments that have found excess counts at low energies. That doesn't mean that we have discovered dark matter. But if you see something that looks like it comes from a certain direction that we expect for dark matter, that's much, much harder to mimic. And I want to stress here that a daily modulation, right, this change in the rate over the course of a day, it's not just the fact that it's modulated with the day. There's really a directional sensitivity. So let me explain this in the context of a different dark matter experiment, the Dama experiment. The Dama experiment has claimed that they see an annual modulation in the dark matter scattering rate. This is something that was expected to be a smoking gun for a dark matter detection. But to date, there's been no other experiment that's been able to reproduce that. And in general, the consensus is that there's probably some systematic that hasn't been well understood here. Why is daily modulation different? It's because it's not just the period of the modulation. It's really also the phase of the modulation. Sorry. So if I build a detector that has two pieces like this at right angles, and I were to measure the dark matter scattering rate from each of these two pieces, I would see a phase delay in the rate between those two pieces. Right? So it's not just that I have a period of a day. It's that I know, because of the anisotropic sensitivity of the detector, that I am getting the highest rate when the detector is pointing its optimal direction towards the dark matter wind. So it's a much more sensitive discriminator than an annual modulation. Okay. Having said that, I now want to build for you how we get this, how we can think about this epsilon tensor and what we can actually do with it. So how do we actually construct it? I have written everything in terms of epsilon so far, right? In terms of the ordinary dielectric function. That's not always the most economical way of writing this formalism. Really, epsilon is just standing in there for a linear response function. So epsilon is one way of quantifying how the electron number density responds to a perturbation. Really, the simplest way of writing that down is with this function chi, which is just epsilon inverse over the Coulomb potential. And the reason I say that's the simplest way is because it can just be written as this 2-point correlator of the electron number density. So given that correlator, I can use standard techniques to compute this or estimate it. So one standard approximation is as follows. I can write down diagrams for this computation at arbitrary loop order. And now ordinarily I would say, in order to get the full response function chi, I should do a geometric sum of all the one particle irreducible diagrams. Well, what if I just drop all of the diagrams except for the one bubble diagram and I only do a geometric sum of those? So I only do all the one bubble insertions and I resum those. That turns out actually to be a pretty good approximation for a lot of cases. That's called the random phase approximation. It also gives rise to something called the Lindhard dielectric function. So I'm going to show you what you get out of this, not because it's especially pretty, but because you can write it in closed form. Here's what it looks like. So now I have an analytical way to estimate the response of an arbitrary electronic system to dark matter scattering. And I want to highlight here a couple of material parameters that have shown up. So first of all, in green over here, there's this plasma frequency that's shown up. It turns out to be the location of a resonance in the material. It has some width. And I now want to show you how your intuition from ordinary E&M carries straight on through to dark matter scattering. So I promised you that screening, electromagnetic screening, would apply to dark matter scattering. And here's what I mean. If you take a system of charges and you try to scatter another system, another charge against that system of charges, right? And the system is net neutral, screening effects will reduce the effective coupling of your scatterer to the material, right? That's screening in a nutshell, that's epsilon. The same is true for dark matter that couples to the electron number density. So here I'm showing you a projected sensitivity curve for two different cases, okay? So here, the purple curve, this is what you would get, this is your projected sensitivity if you don't include the material response. If you just say I have a bag of electrons, I'm able to scatter with any one of them. And there's no response, there's no screening. If you use the Lindhard dielectric function, or equivalently the random phase approximation, you get the orange curve. In cross section, that is less sensitive by a dozen orders of magnitude in the region where we want to be. So this is telling you that screening is not only present in the system, it's actually extremely important. Now, one other thing you learn from this is that the screening effect has nothing to do with the mediator. So the early way, the first way people thought about screening effects in this context was to say, well, if I have a dark photon with my mediator, well, then maybe that photon will mix with the standard model photon. So in medium, I'll have some mixing, and then it makes sense that whatever screening the photon is subject to, the dark matter scattering will be subject to the same screening. But it also works for a scalar, which doesn't mix. So how do you tell by looking at the scalar mediator that there's some kind of in medium effect? It's much harder to do a priori, but what this formalism is telling you is that you really shouldn't be trying to compute it that way. You should be separating between the initial perturbation and the material response. Now, screening hurts us. There is also a collective effect.
How should I understand this if I just couple to electron?
How should you understand?
Yeah, let us say my scalar just coupled to electron.
Yeah.
How should I understand the screening?
With scalars?
Yeah.
It turns out that you can understand.
How a vector maybe B minus L or something. Yeah.
You mean like you're saying because I'm not coupling to the nuclei, so I'm not net neutral?
Yeah.
Yeah. So indeed, it's not exactly the same as E&M screening.
You're still assuming that it's net neutral.
Well, no, I'm not actually assuming that. I mean, it is true that it's electromagnetically net neutral, but here I'm assuming that the dark matter is coupling not to the charge, it's coupling to the electrons. So the rearrangement
only to the electrons.
Yes.
And then why is it screened?
Yeah, it's to say that it's exactly the same screening is, although the material response is the same, it's not quite the same literally. So you're moving around the electrons, right? You're changing the electron number density in such a way that cancels out the applied perturbation. I think the easiest way to say it is just that if you look at the, if you include all the loop contributions from the in medium scattering, that will cancel out. That produces cancellations. It suppresses the scattering. And that is the same ultimately as for the ordinary screening. If you do the computation that way, you'll get the same answer. So screening hurts us. I want to show you now a collective effect that we can actually use to our advantage. And that is the plasmon. So what is a plasmon? If you Google it, as I once did many years ago, you will find out it is a brand of biscuits in Italy for babies. I guess this is part of our proud tradition of naming particles after things on the grocery store shelf. However, what a plasmon actually is a collective oscillation in the electron system. So there is some natural frequency in the material where the electrons are effectively moving together like this, and that gives rise to a nice resonance in the material's loss function, in its dielectric response. So if I show you, for example, the dielectric loss of aluminum, you will see this nice big peak at 15 eV that corresponds to this plasmon mode. A big response corresponds to a big dark matter scattering rate. So this is something that we could in principle take advantage of. Now, I want to make the point that here, if you look at aluminum, you will see that I have data here that I have fit to some model. There is some very nicely fit width to this plasmon. That width can actually be very different between different materials. And here on the right, I'm showing you what this would look like for a few different plasmon widths, if it wasn't just the one that was taken from the experiment. And what you can see here is that at low energies, that width can make a very large difference in the response function. I would encourage you not to really look too much down here, because the picture that I'm showing you sort of breaks down at these energies, and we shouldn't really trust that this green curve is above the blue curve over here. But you can see that still over a very wide range of energies, the width of the plasmon is making a difference. And that's actually really important, as I'll explain in a moment. Okay, so here I want to take a moment just to give you some summary of what we have learned from the Lintard function. So one is that screening is not some model-dependent feature that comes from dark photons mixing in medium. It is a generic feature of material response. The second is that there are these plasmon resonances that enhance the scattering rate. And third, that the width of those plasmons can be quite important. So,
sorry, can I ask one thing?
Please.
So the X scale on the left plot goes up to 1 GeV, right?
Correct.
So you still have screening also for at those?
Yeah, you do.
Two order of magnitude suppression of the sensitivity?
Yeah, so this is for an aluminum superconductor. I don't know what this curve would look like for some semiconductor that's at a GeV, but there are considerable uncertainties that already come into play at the GeV scale. And I'm actually, that's why I want to make this point about the width of the plasmon, because it turns out to actually play a big role in exactly that uncertainty. So takeaway is that we have this analytical form of the dielectric function that we can now use to make some heuristic statements about what makes for a good experiment. So what does it look like? Well, here's a cartoon. Here's a real visualization of what the loss function in a material looks like. This isn't very easy to read, so I want to reduce it to a cartoon for you. So in cartoon form, here's the same thing I just showed you. On the horizontal axis is the momentum transfer. On the vertical axis is the energy deposited in the scattering process. And I want to highlight a few things on this plot, but first I want you to pay attention to nothing except these three wedges. Right, so this wedge, and this wedge. Those are the kinematically accessible regions for dark matter particles of three different masses: 100 keV, 10 MeV, 1 GeV. So those are the portions of the plane that dark matter can access. Now, if you look at that gray band over there, that is essentially my attempt to draw a contour of what the loss looks like without the plasmon contribution. And then in blue is the plasmon. So remember, before I showed you this plasmon peak, it was a nice peak in energy. That was a vertical slice through this plane, right? So we were looking at a slice that went like this. If you expand it to the full energy momentum plane, it looks like some band over here. Now, I want to point to that region, right? So that is where the plasmon width can be particularly important. You can see here, this plasmon is something that has parameters that are reflective of aluminum, but it's also sort of what you would expect for something like silicon. And the width over here of that plasmon is getting so big that it's starting to leak into the accessible region to the dark matter. So this is a region where you might actually have substantially enhanced scattering relative to what you would expect because of that plasmon contribution. But you can also see from this plot that there's basically nowhere else that you can see that blue plasmon. It's not entering the kinematically accessible region anywhere. So if we want to identify targets for dark matter scattering that are going to perform well, we want to find targets that can access the plasmon. It turns out that this is pretty easy to do. What you need to have is you need to have something that can reach the plasmon before it goes away. If you just combine some pieces of kinematics, you can convince yourself that there's a simple rule of thumb. The Fermi velocity in the material needs to be lower than the dark matter velocity. Okay. This is somewhat unfortunate because Fermi velocities in typical materials are 10 to the minus 2-ish usually, and the dark matter velocity is 10 to the minus 3. So if we happen to be in a bigger galaxy with a faster dark matter, maybe we'd be better luck. But we could still look for a target that has a low Fermi velocity, and one such target might be a heavy fermion material. So what's a heavy fermion material? This is a material where the effective electron mass at the Fermi surface is actually set by collective effects and is not just the bare electron mass. And because of that, at fixed Fermi momentum, the Fermi velocity will be lower. And it turns out that if I show you the plasmon in a heavy fermion material, it looks like that. It's the orange band. That's the plasmon in a material called uranium ruthenium silicide. And you can see that it's actually accessible to dark matter scattering at masses of order 100 keV. And in fact, if I show you projected reaches for a bunch of different experiments, uranium ruthenium silicide, that heavy fermion material, that's the green curve. So you can see that up here at GeV scale, it's a hopelessly poor performer, but at 100 keV to 10 keV, it's actually doing really well. In fact, better than aluminum.
How big is the detector?
This is a projection for a kilogram year exposure, which is large for current purposes.
How much is this stuff that we have?
Oh, the uranium ruthenium silicide?
Yeah.
Okay. One should not, although it has been well studied for condensed matter reasons and it can be produced in quantity, one should not use it for a dark matter experiment. Can you think why? Please.
There is uranium.
There's uranium in it. It's radioactive. Okay, so we shouldn't use that for a dark matter experiment. This was just the first material that came up when we Googled heavy fermion material.
In the lead boxes. I'll probably create as a background.
So exactly. So this was just what kind of tipped us off to the idea that maybe there are heavy fermion materials where we can really easily kind of bootstrap and understand what the sensitivity would be. However, this leads to a much broader idea. And now I want to kind of transition to talking about how to take advantage of all these things I've just told you to really identify systems that make for good detectors.
But just a quick question
Please.
before you go. Why in this case your aluminum band is so different? Sorry, the constraint from aluminum is so different from silicon? I thought you.
Oh, sorry. It's because you're talking about this cutoff over here.
Yeah.
Yeah, it's just a feature of the plot I didn't explain, that the silicon is shown at the 2e minus threshold. So this is the threshold for this one is to be able to liberate 2 electrons, and the aluminum is projecting forward to a superconductor that has a really, really low gap. So the thresholds are different, but you can see that where the energy is well above threshold, the two agree pretty well. Yeah, thanks.
But what about the plasmon? I mean, the plasmon is 15 eV, right? So it's many electrons.
Right. So
That's
indeed,
per
if
year.
you get an enhancement from the plasmon in
Which is not here then.
right, exactly.
Okay.
Exactly.
So it's not in this plot. Then.
yeah, exactly. Well, it's being incorporated. It just doesn't make that much of a difference. and it makes the same, to the extent that it makes a difference, it makes the same difference for aluminum and silicon. It's basically, it's the fact that that this piece over here is just barely leaking into the accessible region. So now let's take all of these ingredients together and let's see what we can come up with. So we don't want to build a dark matter detector out of uranium. We've established that. What else could we do? Well, the first thing I want to suggest to you is that this heavy fermion effect that I just showed you might be most useful not for enhancing the overall sensitivity, but actually for introducing anisotropy in the system. In particular, what if we had a heavy fermion that was only heavy in one direction? Then there'd be some parameter space where the dark matter would get an enhancement to its scattering rate just in one direction, and we'd have a directionally sensitive experiment. This turns out to actually be fairly common. So if you look at real materials, there are plenty of materials that actually have large ratios in their effective masses in different directions. So black phosphorus is an example that has a ratio of order 10. Bismuth actually has a ratio of order 100. So these systems already exist in nature. Let's see if we can model what the response looks like for these systems. So I want to real quick remind you how we get that response function chi in the isotropic case, right? We do this trick with the insertions of all the bubbles, right? And that gives the overall response function, the linear response, in terms of this bare response function. That's the one bubble diagram, right? So this is just the geometric sum of the single bubble. The single bubble looks like this. Now, if I want to do this in an anisotropic way, what I have to do is replace the dispersion relation for excitations in this system. So instead of just q squared over 2m, I'm now going to have a directionally dependent mass. And now I can basically do a nice mathematical trick where I transform this to be isotropic in k-space again. So I'm going to introduce new coordinates for the momenta. It's capital Q. That's going to be related to the ordinary Q just by basically m over mi. And by going through a couple of steps here, you can convince yourself that all you have to do to get the anisotropic response function is to take the isotropic one and put that big Q in instead of little q. That's, again, the single bubble. That's the bare response function. And you have to put it back in here to get the full RPA response function. Okay, that makes it very easy to compute. Let's see what we get. So the first prediction we should make is that we will have a plasmon which is substantially different between the two directions. So in particular, the heavy direction should see a plasmon that sits lower in this plane, just like with the uranium ruthenium silicide, and the other direction should be light. So this means that there should be a plasmon which is visible to the dark matter in one direction and not visible in the other direction. If we actually go ahead and compute the full loss, here's what it looks like. So again, this is energy and momentum transfer. That is now the portion of this plane that's accessible to the dark matter. There's a low electron mass direction and a high electron mass direction. And that blue band is the plasmon. So you can see that indeed, between these two directions, the plasmon is moving from outside the accessible region to inside the accessible region. And that leads, for this system, where I've assumed a ratio of 20 between the two directions, this leads to a very substantial daily modulation in the scattering rate. This is like an order 1 modulation. Now, I want to make a point here. What I just did was with an invented material. It was imaginary. I said, imagine I have a material that has this mass ratio between this direction and that direction. We can actually do better than that, because now there are actually databases, computational databases of materials that have been studied in DFT and similar formalisms. So we can actually borrow computations from the condensed matter literature to do this in an actually data-driven way. So there is a project called the Materials Project that is computing properties for an enormous set of materials. So they actually have about 150,000 materials in their data set overall. And they have, for 1,000 of those materials, they actually have dielectric tensors. And they have the full tensor. They have them in different directions. Now, they only have them at low momentum transfer, but that's still pretty good. That's a really good starting point for us to ask what kinds of materials might be the right systems for directionally sensitive dark matter experiments. Now, as a technical point, we do have to deal with this fact that they only compute the dielectric function at low momentum transfer. So there's a way of sidestepping that. What we do is we
Sorry, I just wanted to make sure you
Yeah.
are again saying that this tensor itself doesn't depend on mediator.
the tensor is a property of material response. And as long as you have a scalar or vector mediator, as long as you have a spin independent interaction, that's right, doesn't matter.
But let's say if I don't know, I mean, so let's say I have a scalar and a vector mediator. They give you the same
Yes.
and only independent of coupled to electron and or coupled to anything.
No, this is strictly for the case where they're coupled only to the electrons. The moment you introduce both an electronic and a nuclear coupling, things do change a little bit.
Well, it's only neutral when for photon, it's only neutral if you include the nucleus.
Yes, so for photons, this is a good example. So why is it that this makes any sense when the photons we know are scattering with the nuclei? It's because the electrons are responding in the system and the nuclei are really not. The nuclei are effectively static at these energies.
Right.
So when you compute the response for a photon, you can include only the electrons and you get a really good answer. What really changes for the dark matter is that once you start interacting with the nuclei, you can also excite phonons, right? You can also deposit energy in the nuclear lattice.
But presumably the nucleus play a role in the screen or not.
Not in a mobile way. They are just staying put.
Okay.
What you're trying to get at is that the medium has to be net neutral in some sense for screening to take place, right? And it's true that the nuclei are there. It's just that they are. Yeah, I think I understand the confusion. So I had said earlier that I wasn't assuming that they was net neutral. No, I am assuming that the system is net neutral at the end of the day, right? But I'm not assuming it when I'm writing down these diagrams. So
But the thing running in the loop are electrons,
yeah,
not.
yeah, that's right. We're only interested in the electronic response. Yeah. Okay. So I wanted to make this technical point about recovering the behavior of the dielectric function as the momentum transfer departs from zero. The way that we do it is we actually fit a combination of the RPA or Lindhard dielectric function to certain features in the data. And there's a couple of benchmarks that we do to make sure this actually makes sense and works well. It does, it actually works quite well. So we're able to start from that small Q data, and we're able to then bootstrap up to arbitrary momentum transfers. With that data, we're then able to immediately look at different mass ranges and look over all 1,000 materials and say which materials will first of all give us the best sensitivity to dark matter scattering in the isotropic sense, and which materials exhibit the greatest anisotropy. So on the bottom plot is the ordinary isotropic scattering limit. All right, so this is just cross-section that you would be able to constrain. Here, there's some fairly generous assumptions, no background, large experiment. And in the top panel is the anisotropic scattering reach. So what this means, the way this is defined, is what cross-section do you need before you would start to see that modulation statistically? And what you can see is that, first of all, we're able with some of these materials to reach almost the same cross-sections with directional sensitivity as we are with isotropic sensitivity. And that's just reflective of the fact that we have a very sizable modulation in the rate. So if we have an order 1 modulation, we should expect to reach almost the same cross-sections with directional sensitivity. It's always going to be lower than the isotropic sensitivity because you need to see many events to establish that they come from a particular direction. You will also notice that there are some materials that are actually showing up at quite low energies with a great deal of anisotropy. So this material over here is appearing both in the anisotropic and isotropic panels. This is rubidium tetrakis zinc triarsenide, and it's a material that's been studied for its properties as a thermoelectric material, but it's never been considered for a dark matter experiment, and it seems from here to be one of the best materials you could hope for a directionally sensitive dark matter experiment. Now, I want to emphasize that this plot is preliminary, and the reason it's preliminary is because we are engaged in a very active back and forth now with our collaborators at the materials project to try to understand, do we understand each of these materials I'm showing you in the plot well enough that we can say they'd be good enough for a dark matter experiment? So things may move around a little bit as this plot gets finalized, but we have at this point a pipeline for evaluating materials for dark matter searches. We've done it now for 1,000 materials, and there are 150,000 others that we expect to be able to do this with. So,
sorry, but what type of background did you assume?
here on these plots, I'm assuming zero background.
Zero background.
Yes, that's just so that we have a kind of reference for comparison. But please come back to that point, because later I'm going to show you, actually very shortly, I'm going to show you some results from a real experiment where those backgrounds become more important. Okay. So the next control handle that we have is not just the material itself, but how we use it. So we've been assuming in everything that I've told you so far that the target is a bulk volume. And that's generally not true. In a real experiment, especially for these prototypes that are right now running in the lab, often you have thin film systems where the size of the system actually becomes important. And here, the way to really understand this is just to say, I'm totally entitled, once I have that dielectric response function, to go ahead and use Maxwell's equations. I can write down the differential equations for the electromagnetic potential, and I can then say, once I solve those equations with the boundary conditions, how much energy is deposited in the material. It turns out that there is a substantial correction whenever the momentum transfer is such that the length scale associated with that momentum transfer is large compared to the size of the layer, right? So if the momentum transfer is really large, if the Q is large, so the size of inverse Q is small, it's all in the layer, it looks bulk. If Q is small, so that inverse Q is large, now you're probing the structure of the system. Now, this effective loss function that you obtain this way has some really interesting features. Let me show you. Here, again, we have energy and loss function. Here, the energy is in units of the plasma frequency, in units of the ordinary plasmon resonance. And you can see here that at high Q, which is the bulk limit, you have a peak at the ordinary plasmon. Looks good. In the thin layer limit, you have the opposite. You have a very, very strong peak that goes off to low energies. And that's exactly what you want for a sensitive dark matter experiment, looking for dark matter at low mass. You want a big response at low energies. So you could ask, by the way, is there a way of actually mixing up materials in a way that gives you favorable boundary conditions to give you the best possible responses? That's a great question. Ask me later in the year. But for right now, I want to focus just on the kinds of systems that are actually showing up in the lab, these kinds of thin layer systems, and I'm going to show you how they actually manifest in our real experimental results. So a couple of key points for detector systems. First of all, you want a strong dielectric response at low energies for light dark matter. You can get this enhanced response due to the geometry of the system. You want a low background rate. You want some kind of anisotropy, either in the material itself or in the geometry of the system. And you need detectable excitations. And this is where we have to transition to talking about real systems. So ordinarily, you think about the direct detection process as the dark matter inducing some measurable transition in the system. What is that transition? You could say it's ionization if you have an atomic target or a semiconductor, but there are many other processes that you might look for. And so now what I want to do is switch to talking about one example of those detectable excitations that have been driving some of the low mass sensitivity in the laboratory. And these are with superconductors. So how does a superconductor work for this purpose? Heuristically, what's going on is the breaking of Cooper pairs. So in a superconductor, you have pairs of electrons that are bound with this attractive interaction that comes from phonons. That leads to a small gap in the material. That gap is usually of order millieV for something like aluminum. So this is a small gap system. What do you get when you break those Cooper pairs? Well, to explain that, we need to do a little more detailed treatment of the superconducting vacuum. So really what's happening is that you have a condensate of Cooper pairs. And when you diagonalize the Hamiltonian in that superconducting vacuum at low temperatures, and you find the elementary excitations, it turns out that the elementary excitations are linear combinations of electron creation and annihilation operators. So these Bogoliubov quasiparticles, which you can think of as kind of a superposition of an electron in a hole, these are the elementary excitations that you produce. And the process that you are looking for is dark matter causing a transition from the superconducting vacuum state to a state that has two quasiparticles in it. They're fermions, they're always going to be pair produced. Now, in practice, how do you really build a superconducting detector? The kinds of detectors I'm going to tell you about right now are of a kind called superconducting nanowire single photon detectors, or SNSPDs. So these are detectors that have been used a lot in photon detection, as the name suggests. The way they work is very similar to, if you're familiar with like a transition edge sensor. You have a superconductor which is held at a current so that it's almost ready to transition. And then any additional energy will cause it to transition to the normal state. So let me just give you a cartoon of that. You've probably seen a picture like this of how the resistance of a superconductor depends on temperature, that at low enough temperature, you just enter the superconducting phase. Really, the phase diagram is a little more complicated. So here I've added the dimensions for magnetic field and current. So if you put too much current through a superconductor, it'll transition. And we sit right here, just inside the superconducting phase and current. And then if something heats up a spot on the detector, that spot will go up on the page. It'll transition out of the circle, and then it will become a little spot of normal metal. But now if I have a little spot of normal metal, all my current is going to flow around that normal metal spot. So the current density will increase everywhere else. And that pushes us this way, and the whole wire becomes a normal metal. What's really nice about these detectors is that they're really, really low noise. They have extremely low dark count rates. And my experimental collaborators actually have built one of these for a dark matter search, which has which is low enough background that it can really set non-trivial limits. So I'm going to show you results from this experiment in just a second. It is a next generation demonstrator with a effective threshold that's 11 microns. So that's about 0.1 EV. We gave this experiment a name. It's called the quantum resolution optimized cryogenic observatory for dark matter incident at low energies. Originally, it had a different expansion, and I couldn't remember it, so I made up a new one. And it is an SNSPD that is still prototype scale, so it's a very small experiment, hundreds of microns in scale. We had a 415-hour science run. In that run, we had 15 counts. Okay. That turns out to be enough to set world-leading limits on light dark matter. So I highlighted before the geometric corrections to the dark matter scattering rate. That is absolutely important here because the crocodile nanowires are actually, they're kind of like flat wires. They're like, think about like rice noodles that are flat, right? they have a layer of superconductor that's only 2 nanometers thick. So if you then compute what is the momentum at which I will start to resolve that structure, it turns out that you will have important geometric corrections for momentum transfers that are less than a few keV. And that translates in turn to dark matter masses below roughly 1 MeV. So that's important. And now we have to come back to anisotropy. So in this detector, it was not originally designed to have any directional sensitivity. We thought this was going to be an isotropic demonstrator. Then we realized that because it has this geometric structure, and because there is this strong geometric correction at low dark matter masses, it actually has natural anisotropy. So in some directions, you're only probing the length of the wire, and it looks like a bulk system. In other directions, you're probing perpendicular to the wire, and it looks like a thin layer. So what this means is that there is actually, if you compute the dielectric response, you will see that as a function of energy, the structure of the loss function depends on the angle at which the incident momentum is coming in. So you can see a considerable anisotropy here. That turns out to lead to this very nice daily modulation curve. You can think about this like a daily modulation curve. Really, I'm showing angle here, not time of day, but you can see that as I rotate the direction of the incoming particle, the effective scattering rate modulates at sort of the 10%-ish level for dark matter masses of 1 MeV and below. Now, with that in mind, I can show you the actual results we get. So here, the top of the plot is overburden. That's our estimate of where, just because of atmospheric overburden, dark matter particles would never reach the detector. The blue curve is the previous generation of demonstrator experiment. And you can't really see the terrestrial curve because of the gray color on the projector, but it runs somewhere like this. That's other dark matter detection experiments that have much larger sizes, but somewhat higher thresholds. And the green curves are the new constraint that comes from the crocodile experiment. And in particular, I want to highlight this dot dashed curve. That dot dashed curve shows the sensitivity that we would have to a directional signal. Meaning, if the dark matter had a cross-section of 10 to the minus 24 centimeters squared, we would be able to tell not only that it was there, but we'd be able to identify that it's coming from the direction one expects. That is extremely important for future experiments because of backgrounds. So if I look ahead, I want to build a bigger version of this experiment. I mean, this projection that I'm showing here, that dotted orange curve, that is assuming an array of detectors that's 10 million times larger. And before you tell me that's insane, there is already an example of 100,000 detectors like this that have been multiplexed, so it's not that far off. But we also want to go to lower masses. There's already a prototype device that my collaborators have in the lab that has a threshold that's about 3 times lower. So the next generation of experiment could in principle probe that entire orange region. The spoiler is going to be backgrounds, right? So if we have enough background that we're already seeing 15 counts up here, what's going to happen as we go down? We're going to see an enormous background, right?
What's the background coming from?
We have some ideas, but we're not 100% sure. So it's possible that it's coming from just electronic noise, but we don't really have a great way of identifying that. It's possible it comes from cosmic rays. We don't really have a great way of estimating that right now.
You can't put them deeper underground.
We can, and actually we're doing it. So we have a spot in Gran Sasso now, and we're gonna do this underground and see if that mitigates cosmic ray.
Sorry, can you comment about the directional sensitivity? I didn't get it. So you are seeing 15 events, and the modulation would be 1 event.
Oh, yeah,
So
yeah.
are you
let me
expanding
clarify.
to a much longer exposure with respect to?
No. What I'm saying is that had the dark matter cross section been up here, we would have been able to see that with directionality. So the fact that we see 15 counts means that the dark matter could at most have this cross-section, which means that if it had this cross-section, we would have seen 200 counts, right? And then we would have been able to establish direction. Does that make sense? Yeah.
I mean, if your background,
If
so the, when you're placing a limit, right? It really depends on the amount of modulation that you expect. If you have a 10% modulation, you know, if you have 100 events, you are not gonna see it. So you are placing the same limit. So it doesn't help.
exactly. So for the purposes,
daily modulation will help if you have a signal.
Yes.
To find out, right?
you are
If
it's perfect. You're taking the words out of my mouth, because what I was about to tell you is that if you look at these curves down here, you'll see that if we have no backgrounds at all, you could reach this dotted orange curve with that futuristic array I'm talking about. But if you did nothing to mitigate the background, you would be hopelessly limited, right? That is actually a case where the directional sensitivity allows you to set a better constraint on the overall dark matter cross-section. So up here, because we see so few events, the directional curve is above the limit curve. Down here, the directional curve is well below the background limited limit curve, just because we would see more events. So
I have another question. I mean, I
Please.
don't understand your overburden, because the overburden should be much lower than that. It's at 10 to the minus 27 in this energy range, and then so I don't understand why you have put it up there. I mean,
It-
that
it
limit
varies with,
is excluded.
it varies with the dark matter mass and with the mediator type. So for like a heavy mediator, I think it is a little bit lower at those masses.
You know, I know very well how much it is because I calculated it, and it's for 1 MeV is around 10 to the minus 27. So you are off by orders of magnitude. I don't know why, but
I'd love to see your calculation, because I'm using a reference calculation from who did the calculation? I'll find the paper later. And that's kind of where I had taken this estimate from, but I'm very happy to look at this, because you know, one of the challenges with a light mediator, as you know, is that you have many soft scatters, and so you need to do some kind of Monte Carlo to estimate the overburden. So I wasn't something I was going to do myself, so I was drawing from literature, and that's what I found. But very happy to look at your paper as well. Okay, so I'm just about out of time. I'm going to throw in one more remark here, which is that everything I have been telling you about so far is for dark matter scattering with electrons. As it turns out, you can also take advantage of these same systems to look for dark matter scattering with nuclei. And that's just because the same exact physics applies. So if you look at a superconducting detector, it's not actually sensitive typically to just two quasi-particles being produced. Really what happens is that you have dark matter that comes in, it produces a quasi-particle pair, those quasi-particles will brem off phonons, those phonons will pair produce more quasi-particles, so on and so forth, and in the end you have a giant mess of quasi-particles and phonons. Now, if you have a lot of these down conversion processes, then the final state is pretty much insensitive to what the initial excitation was. And in particular, whether that initial excitation was a quasi-particle or a phonon. So what this means is that as long as you can compute the phonon excitation rate, and you can do that using some inputs that I won't describe right now, you can then immediately project what you are sensitive to in the nuclear couplings. So here, I'm going to actually skip this real quick. I'm going to go straight to here. So this is for, again, the crocodile experiment. The green curve is showing you the limit on nuclear scattering. And here, you should note that the green curve is outperforming this dark gray region that I've labeled as elastic, and it is not outperforming this light gray region that I've labeled as migdal. Why is that? Because elastic nuclear scattering is basically the process that we are probing over here. The migdal effect, in which a nuclear excitation is converted into an electronic excitation, has the more favorable electronic kinematics. Now, as it turns out, that's probably something we can actually achieve with the superconductor as well. So just as in the Migdal effect, dark matter bunks the nucleus and the electron goes flying out, similarly, in a superconductor, you could have this process where you have basically an off-shell phonon that produces a quasi-particle pair. So that's something we're working on right now. I'm going to wrap it up right here. I just want to leave you with a couple of takeaways. First of all, that we have these new tools for thinking about how dark matter should scatter in condensed matter systems. We have tools for taking advantage of large data sets that the condensed matter community has produced to actually build effective detectors that have new capabilities. And we have real experiments that are actually implementing these ideas and that are hopefully showing us it's not too far off to probe real cosmologically interesting parameter space. So I'm going to leave it there. I sit in 351 while I'm here. I'll be here through probably most of the day tomorrow, and I'm happy to take any more questions now. Thanks, everybody.
No questions?
In the second point where you were looking for these materials in the repository, did you find any that was promising and also could be produced on that scale, and you can have a large experiment with it?
Yeah, so actually one of the materials that looks really interesting is, I'm not going to pronounce it correctly, but it's lithium oxygen, lithium molybdenum oxygen something. And it's actually a really common material for batteries. So it's been produced in bulk. Yeah.
Yeah, I want to go back to the daily modulation in
Sure.
particular. At the beginning, you mentioned, you calculate this epsilon for different material. I remember in some of the original paper by Ruben Essig, there is a mention about silicon when all this started, and that there is an anisotropy, but then this was not followed up in any other paper.
Right.
Is because that is so small that is irrelevant, or because, so did you look at that?
Yes.
I mean, before looking at this very elaborated
Yes,
material.
yes.
If you look at silicon, which, we are already using for very sensitive searches,
Yes.
how much is the anisotropy there?
Great. So one thing I didn't mention is that, in fact, many materials have some small degree of anisotropy, including silicon. It's too small to be that useful for a dark matter experiment. The real problem, though, is just that most of the silicon you get isn't a single crystal, it doesn't have consistent crystal axes over the whole sample. So if you take a random chunk of silicon, it's going to average out.
I don't agree on that. Yeah.
If you have a nice pure sample where everything is aligned, then you can do it. I think it's of order 10% in the masses in different directions, if I remember correctly, for silicon.
So this has been calculated?
Yeah, I don't know if we put it in our paper, actually. We definitely calculated it.
I don't think so.
Yeah, I'm happy to dig it up for you.
Because that is relevant for existing experiments.
Yeah.
It is 10%, is very valuable. Because, there are daily modulation measurements.
Yeah. No, I'm happy to dig that up for you.
Okay, there are no more questions. Let's thank Ben again.